Hello and welcome to this video on truth functions part 1. In this video we are going to go over how to compute the truth value for a compound or complex statement. And from now on I'm pretty much going to refer to statements as propositions because logicians have a specific technical word for statements, and that's the word proposition. So if you hear me using the word proposition, I mean statements. They're the same thing. So with truth functions, we're going to be able to determine the truth value of a compound or a complex proposition. And that would be the case in which we know what the truth value for the parts are. So because we're talking about compound or complex propositions, that logically implies that there will be components to those complex parts, right? All complex things are composed of simpler ones, and that's basically what's going on here. We start with negation, which is already complex because it already involves a connective. It already involves the tilde, which remember is a logical function, and so in that sense negation is already complex or compound. And then we'll move to conjunction, disjunction, and then in our next video we will do what's called the biconditional, which is the triple bar. And also in this video we're going to do the conditional. So we're going to do negation, conjunction, disjunction, and the conditional in this video. Okay, so let us start with negation. And as I said just a little while ago, negation is the simplest one of these, but the negated statement is already compound or complex in some sense. So what I have here on the left is basically the two possible truth values of P. I'm using lowercase p here because in this case we're talking about any proposition. I'm going to talk about I'm going to refer to the proposition John goes to the movies here, but I have not symbolized John goes to the movies, and I did that on purpose. That's because whatever results we get for the not p or the tilde p, whatever truth values we put under that, and this will be true for all of the ones that we go over for conjunction, disjunction, and implication, is going to apply to any proposition. So that's why this is going to be a lowercase p, because this is in a sense a variable. Whatever we come up with here will apply to all propositions. And I'll explain that as we go along, but don't think in terms of a specific proposition here, because whatever we come up with as a ultimate truth value will apply to all propositions. So if we think about John goes to the movies, it is an assertion, right? It's an affirmation. We talked about affirmations already, that they are kind of a yes saying. So there are only two possible truth values for that affirmation, and that's what we have under the letter P. We have T and F, T to represent true and F to represent false. Well, if it's true that John goes to the movies, which is what we have in the first row, then the opposite, John does not go to the movies, which would be the tilde P, right, will be false, right? So under the tilde P, we have false. And let me actually write out what the tilde P means, what it's representing in this case, right? So P in this case is representing John goes to the movies. Not P will be representing John does not go to the movies, right? So let me put that over here on the left. But remember, this can mean any proposition, and that's why it's a lowercase p, because whatever we come up with here is going to be true for all propositions. Basically, if P is true, not P is false. This will apply to any proposition. Okay, so not P or tilde P is John does not go to the movies, and so again, if P is true, tilde P is false. Okay, well, if John does not go to the movies is false, and if that means that John goes to the movies is true, right? Well, what would happen if it's false that John goes to the movies? That's the case we have in our second row here. What happens if to begin with it is false that John goes to the movies? Well, then tilde P would have to be true, right? And so that's why the truth value of the compound or the complex here is T, right? If it's already false that he goes to the movies, then it would be true that John does not go to the movies, right? And that's because it's the opposite, right? So if it's already false that he goes to the movies, then it would be true. John does not go to the movies would be true. So with negation, we're basically dealing with opposites. If one is true, the negation of that proposition is false, and vice versa. If the proposition is already false to begin with, then the negation would be true. Okay, so that's actually the simplest one. That's negation. Let's go to conjunction. Here we have the conjunction, John goes to the movies and he goes to the beach. So again, think of P as John goes to the movies and Q as he goes to the beach. But again, remember that we're not using the capital letter to represent each because these are specific ones. But think of P as John goes to the movies, and think of Q as he goes to the beach. Okay? So what we have on the left here are the possible truth values for P and Q, right? So it is possible for both of them to be true. That is to say, it's true that he goes to the movies and it's true that he goes to the beach. It's possible that it's true that he goes to the movies, but it's false that he goes to the beach. And then it's possible that it's false that he goes to the movies and it's true that he goes to the beach, right? This is what the third row is representing. And then the fourth row represents the case in which they're both false, right? It's not true that he goes to the movies, and it's also not true that he goes to the beach. Okay, so the question now is, what would be the truth value of the conjunction? Okay, well, if it's true that he goes to the movies and it's true that he goes to the beach, well, then the whole thing would be true, right? And that's the truth value of that compound or complex proposition, John goes to the movies and he goes to the beach, given that both P and Q are true, given that it's true that he goes to the movies and it's true that he goes to the beach. Okay, in the next scenario, we have the case in which it's true that he goes to the movies. So this is now our second row. In this case, and ignore the little spell check from Word here. In the second case, we have then the case in which it's true that he goes to the movies and it's false that he goes to the beach. And so the truth value here would be false. And the thinking here is that if one of them is false, then the whole thing is false, because this is a conjunction. Okay? And so similarly, in the third row, where it's false that he goes to the movies, and it's true that he goes to the beach, then the whole thing would also be false, right? Because what we have here is basically the truth values of the conjuncts are reversed, right? So then the whole thing would be false. Okay. And then the last case is the case in which they're both false, and hopefully that is obvious that if they're both false, then the whole thing is false, right? So think about what's going on here. Overall, if each conjunct is true, if both of them are true, then the whole thing is true. And then if any one of them is false, then the whole thing is false. And then if they're both false, then the whole thing is false. So this is why we have the truth value of the whole the way that it is. And in this case, the whole means the conjunction. Okay, let's go to disjunction. Okay, so here is our disjunction. John goes to the movies or he goes to the beach. Okay, so remember that it is the wedge there that symbolizes the or. This is something that you should know from the last video on 6.1. Okay, then the truth values are over here on the left again. So the scenarios here are the same. We're dealing basically with 4 possibilities. They can both be true. So that would be the case in which it's true that he goes to the movies, and it's also true that he goes to the beach. And then the second case here is where it's false that he goes to the beach, and it's true that he goes to the movies, right? And then the third one here is the case in which it's false that he goes to the movies, but it's true that he goes to the beach. And then the last one is where they're both false, right? It's false that he goes to the movies, and it's false that he goes to the beach. Okay, there is an important criterion here when it comes to disjunction. And the criterion here is basically that at least one has to be true in order for both of them to be true. Another way to say that is at least one has to be true in order for the whole disjunction to be true. So, okay, well that meets that our first row here meets that criterion, right? They're both true. So if it's true that he goes to the movies, and it is true that he goes to the beach, then John goes to the movies or he goes to the beach is also true, right? And so that's why that would end up being true. Okay, well, look at our second row and remember the criterion. If at least one is true, then the whole thing is true. Then the second row will also be true, right? Because we have the left disjunct as true, right? It's true that he goes to the movies. So think about it. If John goes to the movies or he goes to the beach, but he ends up going to the movies, so basically that means that it's true that he goes to the movies, then the whole thing is still true, right? John goes to the movies or he goes to the beach. Okay, our third row is the case in which it's false that he goes to the movies, but it's true that he goes to the beach. Well, again, the disjunction is going to be true because we meet the criterion. And the criterion here, again, remember, is that at least one is true, right? Well, in this case, it's true that he goes to the beach, right? So John goes to the movies or he goes to the beach is true because he ends up going to the beach, right? So we fulfill that criterion. So that's why that is true. Okay, our last scenario here is where they're both false. Okay, this is the only case in which the whole thing is false. If he does neither, if he neither goes to the movies or he goes to the beach, then the whole thing ends up being false. So that is it. That is why the truth values turn out to be the way that they do with disjunction. Notice that things are kind of reversed here. Let me put up conjunction again. Notice that in conjunction we have T, F, 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 and here we have T, 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 F, right? So that might be a way to memorize these. And it is better if you memorize them, because when you are doing truth tables, it's a lot faster if you have them memorized. Okay, the last one in this video is going to be the conditional, which is remember, we're dealing with implication when we deal with the conditional, and so there are reasons why things hold the way they do here when it comes to a conditional. This one is probably the hardest to explain, but I'll explain it in terms of a regularity. So imagine a pool table where balls are hitting each other, and let's just call one of the balls ball A and another ball B. Well, then we understand what is meant when someone says if ball A hits ball B, then ball B moves, right? We understand what that means. Notice also, though, that this is kind of a regularity. And I don't mean a natural law here, like a law of physics, because the laws of physics are much more general than that. But this is obviously something that holds true because of physical laws, right? Because we know the way that these balls work. We know that they are kind of light, right? So such that if one hits the other one will move. They're both very light in that regard. So we understand what we mean by regularity here, right? Basically, if one thing happens, then something else should happen, right? That's what we mean by regularity. So think of the whole as a regularity here. If ball A hits ball B, then ball B moves. Think in those terms, in terms of regularities, which is a little bit like a law, right? Like a rule in nature. Okay, well, let's look at the possibilities here then. So the first row represents the case in which they're both true, right? So ball A does hit ball B. That's what that means. That's what we mean when we say that that one's true, right? And then ball B does end up moving, right? That's what the Q would mean here. If the Q is true, then ball B moves, because remember, ball A here, ball A hits ball B, by the way, is the P. That's the antecedent, right? And remember, the P here on this side of the horseshoe is the antecedent, and the Q here on that side of the horseshoe is the consequent, right? So ball A hits ball B represents P. Ball B moves represents Q. And you don't always need the then, by the way. The then is kind of a linguistic piece. I could also say if ball A hits ball B moves, right? But remember, the whole thing would then be the consequent, and that would be our Q. Okay, well, in our first row, we have the case in which they're both true, right? Ball A hits ball B, and then ball B ends up moving. Okay, well then, what would we say about the regularity? Well, we would say that the regularity holds, right? In other words, the regularity is true, right? Because what we expected to happen did happen, right? Ball A did hit ball B, and ball B moved because ball A hit ball B, right? That's the regularity that we expected, right? So that would make the whole thing true. Okay, let's look at the second possibility here, the second row. Okay, let's think about what's happening in the second row. Okay, so in the second row, ball A is hitting ball B because the antecedent is true, right? And that's what it would mean for ball A to hit ball B. That means that the antecedent here would be true, that it does happen, right? Ball A does hit ball B. Think about what's going on in the consequent. Ball B is not moving, right? Because remember, ball B moves. This part here, ball B moves, is false, right? That's what that's saying. So it is true that ball A hits ball B, but ball B doesn't move. Now you might ask, why? How could that happen, right? Well, it's not hard to imagine how that can happen. What if somebody glued ball B to the pool table, right? Or what if ball B is on one of the edges and just can't move forward, even though ball A hits it? Maybe it kind of it trembles, but it doesn't move. I'm not probably not using the right word here, but it just doesn't move if it's on the edge. But let's just imagine the case in which it's glued to the pool table, or there's a nail going right through it where it just won't move. Well, then that's not hard to imagine, and so it is possible that ball B doesn't move, right? Well, what's happened there? Well, the regularity, if ball A hits ball B, then ball B moves, the regularity doesn't hold, right? So then the whole thing has to be false. Because what we expected to happen, what we thought would happen, didn't happen. And it didn't happen for whatever reason. Ball B was glued. It was there was a nail holding it down on the pool table. Whatever reason it doesn't move. What's important to understand here is that the regularity doesn't hold, and that's why the whole thing would be false. Okay, let's go to the third possibility here, the third row. Okay, so let's think about what's going on there. Okay, so what's going on there is ball A is not hitting ball B, right? Because the antecedent is false, P is false, right? It's not, ball A is not hitting ball B, but notice that ball B is moving, right? And how do we know that? Well, because the consequent is true, right? The Q part here, which is the consequent, is true. Ball B is moving. Okay, the question here again is, well, how could that happen? The person playing pool doesn't hit ball A, right? They just don't do anything. But somebody else maybe taps ball B and ball B moves, right? Or maybe there's an earthquake that only moves ball B. Who knows, right? Or there's a fan in the room and the fan moves ball B. The wind from the fan moves ball B. Who knows why ball B moves? Well, what happens? Would the regularity still hold? Yes. So this one would be true. Why would the regularity still hold even if ball A doesn't hit ball B? Well, think about it. The regularity would have held if ball A had hit ball B. It's just that in this case, ball A doesn't hit ball B and ball B moves for another reason, right? For maybe somebody, again, taps it, a fan in the room moves ball B. For whatever reason ball B moves, the regularity would have held if ball A had hit ball B, right? We can imagine why ball A doesn't hit ball B. It's because the person playing pool doesn't hit ball A, and that's what would make the antecedent here false. But ball B can move for some other reason, and so the regularity is not violated. Whereas in our second scenario, the one we just saw here, the regularity is violated, because in order for the regularity to hold, ball B does have to move, given that ball A hits ball B, right? That's basically what the regularity means here. Okay, so that's why the whole thing ends up being true, because the regularity would hold. Okay, let's look at the fourth and last scenario. So the fourth and last scenario is where nothing happens, essentially. Right? Ball A doesn't hit ball B, and ball B doesn't move. So you might imagine that the billiard players here doing nothing, just sitting around doing nothing, and nothing moves. Okay, well, what do we know about the regularity? Well, is the regularity violated because they don't do anything? No, it isn't, right? Why is that? Well, we know that if ball A had hit ball B would have moved, right? Because that's what the regularity means, right? If ball A had hit ball B would move. And so that's why that would still be true even if both are false. And I know this sounds strange and weird, but think about it logically. The regularity would have held even if somebody does nothing, right? So here it might be useful to think of this as a kind of law of nature. The laws of nature hold. Let's take Newton's laws of physics. They hold regardless of what's going on, right? I know that that my pencil will fall to the ground if I let it go. But what if I never let my pencil fall to the ground? What if I hold on to my pencil? Well, we know that the law of gravity would still hold, right? That's basically what's going on in this fourth scenario. It is the case in which nothing happens, but we know the regularity would hold if somebody did something. And in this case, that would mean if ball A hits ball B. Okay, so that's it. That's why we have these truth values, and that's why they are the way they are. For these compound or complex statements. And so the conditional obviously is a complex or compound statement because it's composed of simpler ones, the P and the Q here. Okay, so join me for my next video in which we will